So I don't know if she announced it, but so I will do a dual session, right, on February 7th, 8th, and because some people want it in person, so I'm gonna do that. And in class, I'm gonna run Zoom so that you guys can all stay home and have it both in person and Zoom. Okay, so February 8th, both in person and Zoom. Okay, KP 108 is the room. Any administrative questions? Yeah, the first midterm one will, I mean, she will make an announcement, but that was the plan. Yeah. Will you continue? I will do it even after the after February, all the way till the end, like of the course, April. So even after. Okay. Yeah. All right. Okay. All right. So let's start with section 5. No, this is 1.2. 1.2 chapter section. Yeah, so let's talk about subspaces. So let me remind you what a subspace is. So if you have a subset W of V, where V is a vector space, where is it? Yeah, then W is also a vector space. Then it's called subspace. Okay, so if W is also a vector space, then it is called subspace. Okay, that was the definition we had. So now let's write down a criterion that is much easier to check. Okay, so like we said last time, this is a very quick way to show that some space is a vector space. So we give you some space and you're like, is it a vector space? One way to do it is you embed it in some other space, which is clearly vector space, like from class. And then, okay, then you can use the following criterion, namely closure. So all you need to check is closure. Okay, so you don't need to check all these axioms. It suffices to check this single axiom of closure. Okay, that's pretty nice, because all the other ones are inherited from the vector space V. Okay, all other axioms. What is F field? Yeah, for here always we have an underlying field for the vector space. So from now on, yeah, whenever we write V, we assume that we're working over some field. Is that okay? Is there a delay or something? Okay. Right, so let's prove that. This is a theorem 128 in your book. So let's go through the proof. One direction is easy. So if you know that W is a vector space, then one of the actions was closure. So going from W subspace to W closure is easy, right? Now we want to show the opposite. We want to show that W closure implies W subspace. Okay. So, oh no, I thought it was me. Sorry. Okay, so yeah, let's so this direction is easy. Let's show the longer one, where just checking closure is enough. All right, so we're gonna go through the axioms. The first, some of them, these algebraic ones, such as AB is A plus B is B plus A. This is commutativity. This was associativity. So AB plus C is A plus B plus C. And this was CAB is equal to CA plus CB. I should use a different letter. This is lambda. Yeah, where lambda is in the field and A, B, C are vectors in W. All right, so all this algebraic things follow from the, oh, I had them, okay. All these algebraic things follow from the ones of the vector space V, right? All these operations are already true, for V, right? So they're also true for W, because each one of them, X plus Y, Z, is in W, which is inside V. So you can do all those operations in V, so you have them in W. Okay. We prove it's a vector space. Yes, now we're proving that W is a subspace, which of V, which just means that, yeah, W is a vector space. Okay. All right. So these three algebraic operations follow immediately because you're a subspace of, you're a subset of V. All right. Let's start with this two. So now additive identity, let me write it here first. So additive identity was 1W plus V is equal, or let me write, yeah, is equal to, let me write X is equal to X for all X in W. No, this should be 0. So you have 0W plus X is equal to X, and you have 1W times X is equal to X as well. So we need to figure out this, these two elements. We need to find them. So, right. So so the claim is that we can take zero W to be 0V and 1W to also be 1V. Okay, so we can use the ones of, yeah, it was 0W, thank you. So we can use the ones of V. So we can use the additive elements and multiplicative elements of V. So let's see that this is indeed true. How do you do this? Well, we know that CX plus Y is in W when Cx and Y, when X and Y are in W, right? This was the closure. So this is known. So we use this. We how do you say it? We know that that Cx is in W, so that implies also that minus Cx is in yeah, is also in W. So the trick we do is we take Y to be minus Cx. Okay, so we take Y to be minus Cx, and then we know that this guy is in W, but then we have distributivity. So here we use distributivity. And then when you add them, you get the zero element of X. I mean, the zero element of the field. Okay. And then here we use one of the properties we proved for vector spaces. We proved this for V, for vector spaces. Okay. And we know V is a vector space. So let me repeat. We know that Cx plus minus Cx is in W because of closure. Then from there, we use distributivity to get that this is the zero element of the vector space, so that following this chain, we get that 0V is also in W. Is that okay? Does claim mean assume or no? Yeah, like both. I mean, same thing. So we can assume it. This is the assumption. We assume that W has closure. It's closed under addition and scalar multiplication. And we're showing that this is a sufficient criterion to get all the other axioms. Is that okay, Ismail? Will additive and multiplicity identity always be 0, 1, or will it be different in some special cases? So this is not like usual 0, 1, right? We're just using this notation, but we always put this subscript to denote that it's special, like it's how you define it. So, you know, we did this example like for complex numbers, right? Like Cn, it's like this, it's the 1, 1, 1, right? I think so. So, or what do I say here? No. Let me see, what do I want to say? Like the one, right. So let's say the 0 Cn is the 0 plus 0 I all the way to 0 plus 0 I. For matrices, you know, is the 0 matrix. So it changes, right, Mima? So yeah, different for different spaces. Okay. Okay. All right, so we showed that the 0 element is still in the space. Okay, so we have the 0 element. Yeah, so we have 0 is in the space. So like an example where you don't have that, we will do it later, is you take x, y in R2, but you fix x plus y to be 1. Here you have that 0, 0 is not in W. So W is not a vector space. Okay, so even though it might look like a vector space, like if you draw this, you get like a nice line and it looks like something you can do operations in, but it's not, it doesn't contain the 0 element. What else? Yeah, and for multiplicative, this follows much easier um, because now you know that the 0v is in your space. You can set any constant you like, so you take the constant 1. So here's what you do. You know, you have that 1f of x is what is it? Cx plus 0 v or 0w, and we know that this guy is in w. Yes, that's one way to do it. If you, but I don't know, I would just say that we know closure under addition, and you can also get it directly, whatever you like. X plus y was supposed to be a vector for the, yeah, that's right. X plus x comma y is a vector. Yes. Yep. A vector in R2. All right. What else? Right. I mean, yeah, in the book, they're further restricted, but we don't really kind of do that. But in the book, they force this condition, Cx plus y to be W, which is kind of redundant, but I might as well talk about it. So to really get closure from this condition alone, so yeah, you have to set C to be 1. So that gives you closure under addition. And then since we just found the 0 element, you can just add it. So you have Cx plus the 0 element is in W. So that implies that Cx is in W, right? So you have C is in the field, you have X is in W. You want to show that Cx is in W. So one way to do it is you just add the 0 element. I mean, that's how they do it in the book. I find it kind of redundant, but I just want to go over it. Okay. All right. What else is left? Yeah, we need to have additive inverse. So that was one of the axioms. And again, we take C to be negative. Okay. We know that this guy on the right is in W. So we want to get back the 0 element of W. And again, here we use distributivity, which we know is true for V, so it's also true for W. And yeah, and then here we use, let me add one more step here. So let me write this as 0V, and then we know this to be 0W. Okay, so because we proved this for vector spaces. All right, so that's the line. We used one of the propositions we proved for vector spaces, right? Is that okay? Oh, Killian, Prof, is it okay to just set y or x in Cx plus y in V to anything for our proof? There are no restrictions to what we can use this proof method for. Right, because there are, so let's be a little bit careful. So the statement was, if C is in the field and X, Y are in W, not in V, but in your subspace, then you have closure. That was the assumption. Okay, that's the criterion. That's the subspace criterion. Okay, so if you know this, you get that W is a subspace. So yes, you can set X and Y and C to be elements, any of elements from W. So you see, we were very careful with how we did them in order. So for example, I did not know that 0v is in W. Okay, I did not know that. I had to prove it. Then once I got that, then I could set y to be 0w. But a priori, I didn't know that. So I had to start by showing this to be true, and then I could do that. Is that okay, Kellyanne? And yeah, the y equal minus cx, we can do that because we have closure under scalar multiplication. So these are good questions. So we know that we have c's in f, we have x's in w, and we have y equal to 0w. Then we have that, you know, I might as well say -1 here, like -1f. So you have -1f x is equal to -1f x plus 0w, which we know is in w. Guess that's one way to do it. Is that okay? So each time we have to, okay, good. Yeah, we have to build from the 0 element, and we have to always write it as an addition, unfortunately. So this is the criterion. We can only write it as addition. So it is what it is. But once we get the 0 element, everything else is pretty easy. The 0 element is really the main issue. All right, so we showed the existence of the additive inverse. We showed that if you give me x and w, I take -1fx, and we showed that this is also in w. Okay, so this is by scalar multiplication. And here we show that indeed it acts as a 0 element. So let me repeat. The additive inverse in V is the same as the additive inverse in W. So all we showed here is that the additive inverse in V is also for W. Okay, that's the idea. Does f come with -1 and 0 by default? Yes. So I think I have the axiom up here. Yeah, so we have 0 and 1, and then we set x to be 1f. So its additive inverse is -x, which is -1f. Is that okay? So this is the additive inverse of multiplicative identity. Great. All right. So, all right. So these were all the axioms. So from now on, please try to use the criterion to show that something is a subspace, and even that something is a vector space. It will save you a lot of time then going through each of the axioms. All right. Okay, so let's go. Let's do some examples. Yeah, so this is the product. So let me start with something easier. So take W to be x comma y comma 0 in R3. Okay, meaning that that x and y are in R. Then pictorially, what do you have? You have that the first two components are filled, but then the third component is 0. So this is the plane, z equals 0, right? It's this flat plane. This is W. And we want to show that this is a vector space. Okay. All right. So we want to show that this is a vector space. And instead of going through all the axioms, we're just going to check closure. So I might as well do it for the general case. So x comma 0 in Fn, where x is in Fn minus 1. Okay, so let's do that. So let's check closure. Take C in the field, take X and Y in F in W. Let me call them U and V. Maybe it's, no, actually, I like it. So let me call this here U. And let me call this X and Y. So we have this, we want to show that CX plus Y is in W. Okay, that's the criterion. All right. So let's see, how are we going to do this? Yeah, so first you write them in this form. So you have C of, what do you have? UX 0, and then UY 0, okay? And we equip it with the same addition. So 0W is 0, plus W is plus V. So since these are elements of the space V, we can add them component wise. Okay, so we have CUX plus UY comma 0. Okay, so can someone tell me why is this a element of W in the chat? Can someone guess? Why is it still? Because it has the 0, that's all. Yeah. So yeah, one is that this is in F, like this is in Fn, and it has the 0 element. So because first is in Fn minus 1, and yeah, we have the 0 element, and 0 is there, still there. Okay. Yeah, that's all. And then do we first have to prove that W is subset of Fn plus 1, or can we just take it for granted, but it looks like a subset? Because how rigorous do we have to be? So let's see. So from here, you immediately have that this is a subset of Fn. And this one, you don't have to do it, because we will always, when you write it in this form, you immediately have it to be in Fn. What else will I say? No, I mean, for this one, you don't have to worry. No, for subset, I mean, I will have to see some other example, but when you're dealing with this specific example of vectors, you do not have to show subset, because it immediately follows from the form. Namely, you have U is in Fn minus 1, and you have the 0 element of the of F, so 0F, right? So you have 0F, and when you put this together, you get an element of Fn, which by definition is every component is from the field. So it just happens that the last element is the 0 element of the field. Is that okay? Yeah, but I wouldn't worry about that. In this case, there are cases where showing subset, like with matrices, it's very tricky. But here is, it's easy. Okay, so we showed closure. So that's it. It's really that easy. Okay, so I should add one more line here that, no, okay, it's fine. It's fine. So what I wanted to say is that you will have to do it by induction. There's a little inductive argument here, namely, how do you know that CUX plus UY is in Fn minus 1? And here you can just mention that Fm for all m less than n is a vector space. So here you can just use a class result that we know that this guy is a vector space. I just want to add this one more line. Okay. All right. All right. What's another example? Yeah. Now this is interesting. This is indeed closed under addition and scalar multiplication. So let me draw it. So we're in R2 and we take this line crossing the origin. Okay, so this is y equal to minus x. All right, so let's show that this is a subspace. So we have to show closure. Okay, let's do that. So take C in the reals and take AB and CD in W. Okay, so what does that mean? It means that A plus B is 0 and C plus D is also 0. We want to show that CAB, let me write it here. So we want to show that CAB, too many C's, call this lambda. Lambda AB plus CD is also in W. That's what we want to show. And that's called closure under scalar multiplication and addition. Again, you take plus W to be plus V. So you can do component addition and component scalar multiplication. So you get lambda A C and lambda B plus D. Okay. And now you have to check that this is in W. So what do? Well, you just take the two components, right? So that was the criterion. You need to, components need to add to 0. So let's do that. We have lambda A plus C and then lambda B plus D. And then what do? You rewrite them. So you have lambda A plus B and then C plus D. Okay. But we know from star, let me call this star, that each of them is 0. So the whole thing is 0. So they are in W. Is that okay? It's really that simple. So try to get practice with this. I'll let you go from step 1 to 2. I should name my steps. Let me see. Are you talking about here? Is this the step 2 or what? No, I mean, why did you add A plus C and B plus D? Why did I add? Oh, because I know that their sum is 0. Right? I know A plus B is 0 and I know C plus D is 0. A plus C. And I added them because I need to check closure. Right? I need to check that their closure is in W. So, right? So just like what was the, oops. So this was the definition, right? That when you add X and Y components, you get 0. So when you add them component wise, you need the two components. You need the two components to add to 0. Does that make sense? Okay, good. Right, so we have lambda A, B, and C, D, and then we group them given what we know, and we did get 0. So we have that this is a subspace. I will leave this as a homework. This is pretty interesting. So as long as you pass through the origin, you don't even have to check closure. So you have something like x1 to xn equal to some c, and this is w. I should just put 0 here. Anything of this form will always be a subspace. Okay, and the proof is very similar to what I just did. Will we ever need to define separate addition and multiplication from V? Will we ever need to define separate addition and multiplication from V? I mean, in theory, let me see. So, but then you won't be able to use the criterion, right? So just to be very clear, the criterion requires you to use the 0w equal to 0v and dot w to dot v. And the reason is that's how we got these axioms like commutativity, distributivity, and associativity, right? We got them because we had this thing here. Otherwise, it's trickier. So I will have to see what the exact examples are. But in theory, yeah. But then it won't really be a subspace of something else. So I will have to see what Lindsay means. Yeah. Okay. All right. Another example is the space of symmetric matrices. So this is a subset of matrices, like let's say M, comma N over the field. Okay. So do I have some steps over here? Yeah, so let's do that. So we want to show closure of symmetric matrices. So what's a symmetric matrix? A simple one is like this, right? So you have 1, 3, and then, but off the diagonal, they're equal, like 4, 4, 6, 6, things of that form, okay? Any that define a unique addition and multiplication. Okay, I will go see what they are talking about. Okay, so these are our matrices and we want to show closure. So it's pretty easy. You use the addition is entry-wise addition. So you start with this CA plus B matrices. So you have C and then you have A1, 1, 1 all the way down, and you add the B1, 1 all the way down, and you do the addition component by component, right? So the first component, you know, it would be like CA11 plus B11, and then same thing for other stuff, right? So CAIJ plus BIJ. So that's a general entry. And then in this step over here, we use the fact that AIJ is equal to AJI and BIJ is equal to BJI. We know this because each of them is symmetric. So you do that, and then indeed you get symmetry for the whole matrix. Okay. So that's the beautiful part about it. So space of symmetric matrices are also a vector space. Okay. Good. Some other very interesting examples include the antisymmetric matrices that we can talk about in when we go into spectral theorem and things like that. And also matrices of zero trace. So like -1, 1, 2, -3, 1, you know, stuff of that form. They're also subspaces. And one way to quickly see this is by embedding them in RNN. And this condition just says that A11 all the way to ANN is 0, right? And we already talked about that this is a hyperplane. So the proof is very similar to what we just did for showing that this is also a subspace. Is that okay? Does that make sense? Yeah, to try to do this as an exercise. This is a nice exercise. Show that the space of matrices with zero trace, namely the sum of the diagonals is 0, is also a subspace. So it's closed under addition and multiplication. All right, great. All right, so what else? Then we have the space of polynomials. So just to remind you, Pn of f are the following. So a0 all the way to an x to the n. And the ai are taken from the field. Okay. So we want to show that Pn of f is a subspace of Pn plus 1f. So first for subset, so since somebody asked, how do you know that it's a subset? So this is an example where you have to do something. You can't just write it down. So this is indeed in Pn plus 1f because you give me any polynomial of this form. You can add the 0 element of the field. Okay, so that's the trick. You add the 0 element of the field, which we showed before that this is equal to 0v. So, okay, I should add a middle step maybe. So let me add a middle step. Let me do it like this. So this is 0v, and then this is your guy. So a0, a and xn. So we start with this element of p and nf, then we add the 0 element of the space. Okay, because we know that Pn is a vector space, or whatever, the Pn plus 1. So we add the 0 element here. Okay. And then what else? Then we know that this guy is equal to this by what we proved in class. But then this guy over here is in the field. It's a coefficient. So this is of the form a0, an x to the n plus an plus 1 x to the n plus 1, which is in Pn plus 1f. Is that okay? All right. So subset is a bit tricky, as somebody asked. So you will have to show that this is indeed a subset. Now for subspace, you just have to show closure. So we take two polynomials, PQ and Pn of f, and we take C to be in the field. In case you haven't seen the summation notation, this just means P0, P1x all the way to Pnxn. And so you write them as a summation, and then you group the coefficients, and then you have that each of the coefficients is in the field. Okay, so this is some other polynomial, h of x, in Pn of f. Okay, So that was the trick here. Is it not much easier? Imagine going through all the axioms. That would have been such a pain. Okay. All right. Let's do another example. So remember we had this func f, which were all the functions from R to R. Let me write R here. Right. So things of this form, like this. And now we claim that the space of continuous functions is a subspace. So it's also a vector space. That's the claim. Okay. So let me do a quick review, first of all, of continuous functions. So a function from R to R is called continuous if you have the following identity, meaning that you fix an element x naught and you take x's coming from the right or x's coming from the left, like this. And then it says that as you do this approximation, like this, so you come from below, so this is f of x naught, or you come from the top. They both limit to f of x naught. So I'm not sure if you've seen this before. So let me write for the first and last time the epsilon delta argument. So it says that for every epsilon, let me write names. For every error, epsilon, like 1/100, say. So for every epsilon, e.g. epsilon equal to 1/100,000, you can find delta number such that x being close to x naught less than delta implies that their images are close to each other. Anyways, I mean, we're not gonna really go into analysis in a linear algebra course, but this is the continuity statement, and this just means this limit thing that I wrote. Okay. All right. I mean, that's what it is. And if you remember from calculus, limits have an additive property. Okay, so you write these two guys, you write them in terms of their limits because you know they're continuous. And here we use additivity of limits that exist. Okay, so then you get that this is the limit as x goes to x naught of some guy h of x, and this guy is h of x naught. So indeed, they are in CR. You have closure under scalar addition and multiplication. Okay, all right. So I have some other examples, but that's more for you if you're interested to look at them. You're not really going to be tested on them. Okay. All right. Thank you so much. See you on Tuesday. I'll stick around for questions. Thank you, guys. Thank you. Have a nice day. Right.
Sorry, can I ask a question, Professor?
Yeah, go ahead.
This is regarding the homework, but like it's a general question. It's not like I hope you can answer.
Yeah.
So for problem 3, it says like, we need to showed that a set is like basically finds operations that makes this set a field, but it just says we have to verify all the axioms in the definition of a field. My question was, how do you do this verification? Because this is a specific field, so I can't really do the stuff that we've been doing here, that like pick a general element. So do I have to like element by element go over and say, okay, this is the additive inverse of this element, this is additive inverse of this element?
Like because you know, you can always ask a private question on Piazza. So
Is that okay with you? Okay, sure.
no, like people have been doing this, and you can do it, yeah, of course. And then yeah, so you have to go element by, yeah, I mean, okay, so
I mean,
let
it's
me.
not big, so doable, but I'm just asking.
No, I
is
know
that
it's
the way
like
to
it was a
approach it?
finite field, right? If you're talking
Yeah,
about
yeah,
this.
it's only 3 elements. Yeah.
Yeah, the
But I'm
F3
asking,
guy.
like, mathematically, is there a better way to do
No,
it?
there's no
Just like
better
how I
way.
learned.
No,
Okay,
no.
so just to verify everything. Okay,
Yeah.
perfect. That was my question. Thank you so much.
Yeah, I can't think of any. I don't know. I mean, how would you do an abstract proof? I don't know if somebody has an okay, it's a homework. Yeah, I'm not sure. Hello, professor. I didn't understand what is the axiom 9 of a field. Axiom 9? What's the axiom 9? Let's go. Yeah, I don't know the number. Like, what is the axiom 9? So I have all the axioms here. Which one was it? Ismail? Wow. Yeah, I don't know what the, okay, let me find this axiom 9. What is the axiom 9? I don't, where was it in the book? I don't remember. Was it 1.1? I guess it's 2 to 4. So 5, 6, 7, 8. So you mean the existence of multiplicative inverse? Is that the one? Huh? Are you there?
Yeah, he's not in the class anymore, Professor.
Oh, he just bounced. Okay, all right. I don't know.
Okay.
All right. Any other questions? No.
Hi, Professor.
Yeah.
Can I ask a question about the reading quiz?
Yeah, of course.
So can I
Yeah,
show?
you can go ahead. Yeah.
Okay. I can't share my screen here. I'm not allowed to.
Oh, I see. How do I do it? Multiple participants can share multi. Okay. Can you do that now?
Yeah, it works. Can you see my screen?
Okay.
So for this question, like, the additive identity for the complex number is, I think it's 0 plus 0i. Is that? But the answer is B. So I'm confused here.
Together with addition in a vector space according to axiom 3. In definition, contains which one of the following is the 0 vector? So did you answer already, or what's going on? Or are you answering now?
No, these are from last week. There are the answers.
Oh, from last week.
last
Okay.
week.
And they don't tell you the, they tell you it's B. Yeah. And
Yeah.
then you said, why did you say C? You said C, right?
Yeah, I think for the complex number, it should be 0 plus 0i, which is equals to 0.
But this is C4.
C4.
C4 is a vector space. It's right? It's like A plus IB, C plus ID, E plus I. Like it's like, you know, like C4, right? We did this in class. It was like CN. You have every component is a complex number, right? Like if that confuses you, forget about C4. Let's talk about R4, right?
Yeah,
like,
yeah.
What's the zero element for R4?
It should be the vector, which is
Yeah, the same thing. It's exactly the same thing. That's why it's B.
why it's the same thing like the C is the complex number, right?
Sorry, the complex number, what?
C is the complex number, but R is
Yeah, I mean, so if you like what B, another way to write B would be 0 plus 0 I. But 0 plus 0 I is equal to 0. So it's the same, like
actually, Professor, sorry to cut in. So I answered none of the above because I thought by 0 they meant 0 in R and not 0 plus 0 I. So we can take 0 as to be both pure imaginary and pure real. Like, is that the thought behind it?
I mean, it's
I
kind
thought
of like
you wrote 0
tedious.
plus 0 I.
Like, yeah, I mean, formally, one should write what we just said. And you can dispute this if you like.
Oh, can I? Like, can I like be like, please?
I mean,
give me
I'm
one
thinking
more
about
time?
it for a second because, like, formally, like, if you really want to be formal, you have to say that the component of I is 0.
Yeah, exactly. That's what I thought. I mean,
yeah,
but
which
I
is kind
understand
of,
also
I
that
mean,
if you
I understand why C, it's tedious to write 0 plus 0, 0 plus 0. But I don't know what to say.
No, but like for this course, if we write 0, is that okay? If based on the context, we mean 0C and not 0R?
Yeah, because like R is a subset of C, so in a way you can write just 0, like 0 is equal to 0 plus 0 I, like, so.
No, I mean, I know, but just like the notation of how to write it.
Oops, yeah, like, but I don't know, like I will, I mean, yeah, 0,
No,
0
it's like
plus,
it's all good. It's all, yeah, it's fine.
but you can fight it.
I mean, this is worth like almost 0%, so it's not
okay,
even...
fine. But if one of you wants to fight it,
I'm sure the professors already have an...
but Hu Yun, are you there?
Yeah.
Yeah. Well, why did you say C though? I'm confused. Like it's a vector.
So I'm also so what I'm thinking is C is the complex number, so it should be 0 plus 0 I.
Yeah. I mean, at the very least, though, it should have been B. I mean, but why? Like I understand D, like none of the above, or B, but why C? Or maybe you thought it's like no.
I think
mhm.
I think 0 plus 0 I can be right as 0.
No, definitely. But why did you say C and not B?
Yeah, I'm also thinking if it's D, so kind of so like for the complex number, the 0 plus 0 I can be right as 0.
Yeah. But this is for complex. Here you have C4.
So C4 is the vector.
Yeah.
Okay.
What
So
did you think was C4?
What I think is the notation C is the complex number. So I'm also regarded as a complex number.
Yeah, but it's a vector of complex numbers.
Vector of complex numbers.
Like like I, then maybe 3I, maybe 4, 1 plus I. Like every component has a complex number. Like,
okay.
Yeah, like I, 1 plus I, what else? 6, 25I. I don't know.
Okay, I got it. So
Yeah.
So so like what if the question changed? Like it's not the C4, but C. So it's
Then it will
moving.
be, the answer will be C, the thing you said.
Okay. Okay.
Yeah.
Got it. Thank you.
Okay, good. Any questions? All right. See you guys on Tuesday.